Each year, more than 45 million tons of glass are reborn from mountains of shattered bottles and jars, turning one of the planet's most stubborn forms of waste into gleaming packaging on supermarket shelves. From broken fragments, glass becomes one of the rare materials that can be recycled endlessly without ever losing its original properties. But how do filthy shards transform into a pure material safe enough to return to the production line? The journey begins at vast, chaotic scrapyards. As soon as it is received, a cascading stream of glass passes through optical sensor systems that scan and sort every fragment with absolute precision. After being cleaned and crushed, it enters the final trial, furnaces heated to thousands of degrees. Here, recycled glass melts more quickly, optimizing energy savings before being reshaped into sparkling bottles and jars filled with the flavors of the world's leading beverage brands. Today, join Agriculture Insight as we step inside one of the largest glass recycling plants on Earth, where scrap is not the end, but the beginning of a sustainable economy. Few people realize that glass, an everyday familiar material, is placing growing pressure on global natural resources. Creating it from scratch comes at a high cost. Billions of tons of sand are dredged every year, causing severe erosion and damage to river ecosystems. Beyond the massive energy consumption and CO2 emissions, impurities in raw sand are also a #1 enemy, aggressively corroding the refractory bricks of million-dollar furnaces. That is why glass recycling has become a key solution for preserving this precious resource. Environmental leaders such as Switzerland and Germany have now reached recycling rates of up to 90%, 3 times higher than that of the United States. Why do you think this enormous gap exists? Many people wonder whether recycled glass is truly clean enough for food use, but the truth is that it is just as pure as new glass. Unlike plastics or rubber, which can easily undergo structural changes, glass is completely inert. It does not absorb odors, does not retain color, and most importantly, does not release any microplastic particles into the human body. That is why, at the strictest frontiers, such as vaccines and high-grade pharmaceuticals, the world still has no perfect substitute for glass, a gold standard for human safety. And now join us as we explore this remarkable rebirth, a journey that may seem vast in scale yet begins in the simplest of places, the household waste bins of millions of families. For this circular process to begin, the first requirement is a stable supply of used bottles and jars. In modern recycling systems, collection largely relies on fleets of specialized trucks, machines designed exclusively for glass. On average, a major operator such as Biffa in the United Kingdom must cover around 3,000 households per day to ensure not a single fragment of recyclable glass is left behind. This pressure becomes even more intense during the summer months, when warmer weather drives up demand for cold beverages. The resulting surge in discarded bottles and jars forces collection trucks to operate at full capacity, making multiple collection rounds per day instead of the usual single run. But door-to-door collection is not the whole picture. In most EU countries, networks of reverse vending machines are now installed throughout supermarkets, activating source-level sorting right at the point of disposal. Consumers simply place an empty bottle into the machine. The system scans it, sorts it, and returns a small cash refund, typically around 10 to 25 cents, depending on the country. A soda bottle you've just finished drinking, instead of becoming waste, can instantly turn into loose change for your next purchase. This approach not only encourages people to participate voluntarily in collection, but more importantly, it supplies recycling plants with a stream of pre-sorted, cleaner, and far more uniform glass than ordinary mixed waste. From here, the journey of transporting tens of tons of bottles and jars to specialized processing plants begins. Large trucks, each capable of carrying between 20,000 and 30,000 bottles per trip, operate continuously. moving between supermarkets and collection points to consolidate the material for recycling. The processing cycle is formally initiated when heavy-duty industrial loaders move in on stockpiles of waste glass rising several meters high. Each bucket can hold multiple tons of material, which is transported in a controlled manner across the yard to maintain a steady feed rate into the plant. At the intake point, the glass is discharged directly into receiving hoppers. Driven by gravity, the mixture of fragments slides down reinforced steel chutes where conveyor systems come into operation. From this moment on, the glass stream, still mixed with sand, dust, and contaminants, is carried deep into the processing line, where successive stages of cleaning and sorting will ultimately determine the quality of the entire downstream recycling process. After being broken down, the waste stream makes its first stop at a multi-stage vibrating screening system. Here, high-frequency vibrations separate natural contaminants, such as dust, gravel, and sand, from the main glass flow. This stage serves as a surface cleaning step, allowing the material to be more clearly exposed and prepared for more advanced sorting processes. However, mechanical equipment at this stage cannot fully remove larger or lighter contaminants, such as paper labels, plastic films, or pieces of wood. As a result, a manual inspection zone follows immediately after the vibrating screens. Specialized workers are positioned along the conveyor belt to visually monitor the stream and manually remove any remaining foreign objects. The combination of mechanical separation and human judgment ensures that the material meets cleanliness standards before entering the more sophisticated downstream separation systems. But even after screening and sorting, troublesome obstacles always remain hidden within the pile of broken glass. Bottle caps. These are the enemies of the furnace, as they do not melt like glass and instead introduce contaminants capable of ruining an entire batch. At this stage, massive electromagnets suspended above the conveyor belt come into operation. Generating extremely strong magnetic fields, they lift and extract every steel bottle cap or screw upward, completely separating them from the glass stream moving below. Thanks to this decisive step, the cleanliness of the material is raised to around 80%. Clearing the way for the critical crushing stage that follows. Once most contaminants have been removed, the glass enters a critical stage of structural transformation. Crushing. Large fragments are fed into hammer mills where high-speed rotating hammers deliver repeated impacts, breaking the glass down into uniformly sized particles. To maintain quality control, any pieces exceeding the specified size are captured by screening systems and redirected back into the crushing chamber. The result is glass cullet with a fineness comparable to manufactured sand. Reducing glass to this granular form not only allows it to melt more quickly in the furnace, but also helps save up to 40% of the energy required compared with using entirely virgin raw materials. Immediately after crushing, the material stream is passed through a high-capacity extraction system. Here, powerful air currents strip away and blow off any remaining microscopic label fragments still clinging to the surface. This final cleanup step ensures the glass reaches maximum purity before entering the laser-based sorting stage. The final, and also the most sophisticated stage in the cleaning process, is optical sorting. At this point, glass fragments are spread thin and allowed to fall like a waterfall in front of a system of high-power laser sensors. In a split second, these sensors scan each fragment to accurately analyze its color and material composition. As soon as a differently colored piece of glass is detected, or more dangerously, a stray piece of ceramic, the system immediately activates compressed air nozzles. These air jets fire with millimeter-level precision, blowing the contaminants out of the main stream in just milliseconds. Absolute precision at this stage is vital, because even a tiny amount of color deviation or ceramic contamination can completely ruin the transparency and quality of the entire batch. After passing the laser system's inspection, The clean glass fragments move along the conveyor belt to the final collection area. Here they are separated and stored individually according to 3 color codes: clear, green, and brown. A step that may seem simple, but in fact directly determines the value and efficiency of recycling. Few people know that clear glass accounts for the largest proportion and has the highest economic value. However, with just 1% colored glass mixed in, a melting batch will immediately become cloudy and unable to regain its original transparency. Therefore, color separation is mandatory to control purity, enabling factories to recycle directly into new products of the same type without incurring the cost of removing color impurities. After being refined, recycled glass cullet cannot be fed directly into production, but must first go through a raw material blending stage. The basic composition starts with pure silica sand to ensure transparency. Next comes soda ash to lower the melting temperature, and limestone to increase the mechanical strength of the finished product. Depending on specific requirements, manufacturers add minerals such as alumina, dolomite, or metal oxides to adjust color and physicochemical properties. In this batch mixture, recycled glass accounts for 20 to 70% of the total weight. This proportion allows the mixture to melt faster, directly saving about 40% of operating energy and reducing carbon emissions compared with using only virgin raw materials. Once the components reach the standard proportions according to the preset formula, the mixture is thoroughly blended and moved to the melting stage. The batch is fed into a high-capacity gas-fired furnace system. Here, the temperature is maintained at around 1,250 degrees Celsius to carry out the material transformation process. Because the heat radiated into the surrounding environment is extremely intense, the operating crew must wear specialized heat-insulating protective clothing and thick gloves to control the melting pot safely. After about 24 hours of continuous firing, the raw material mixture melts completely and turns into a highly viscous liquid. During the next 5 hours, the molten glass is kept at a stable temperature for the refining stage. This is a mandatory step that allows air bubbles to escape, ensuring the purity and uniform structure of the glass stream. To transform the molten glass stream into products with specific shapes, the mold system is an indispensable component. Based on designs created in specialized CAD software, molds are manufactured from cast iron or special alloy steel. These materials possess extremely high heat resistance, up to 1,400 degrees, ensuring they do not deform when in continuous contact with molten glass. After fabrication is completed, the mold sets are installed on the production line, ready for the forming stage carried out directly inside them. When the mold system is ready, the process enters the double blow stage, the standard method for producing hollow containers such as soft drink bottles or pharmaceutical jars. The process begins by cutting the molten glass stream into gobs of uniform weight. These gobs enter the preliminary mold at around 1,000 degrees Celsius, the ideal temperature at which glass reaches stable viscosity, allowing smooth forming. Inside the preliminary mold, a first blast of compressed air is blown forcefully from above, pressing the molten glass tightly against the mold walls. The result of this step is the formation of a parison, a hollow structure in which the bottleneck is clearly shaped, while the body remains soft and retains a large amount of heat. Immediately afterward, the glass parison is transferred to the final mold set, located right next on the production line. Here, a second blast of compressed air is injected directly into the center of the parison, stretching the softened glass outward until it fully conforms to the fine details inside the mold cavity. Although this process appears very fast from the outside, in reality, the entire system of valves and sensors must be synchronized with precision down to 1/1000 of a second. It is precisely this extreme level of technical control that enables corporations such as Coca-Cola or Heineken to ship hundreds of thousands of bottles every day with absolute uniformity, ensuring that every single bottle meets the same standards before global distribution. Although today glass packaging accounts for only about 15% of Coca-Cola's total output, it is by no means outdated. On the contrary, for many discerning consumers, glass remains an irreplaceable choice. It keeps drinks cold longer, does not retain odors, and does not alter flavor. As a result, the fizz and sweetness are preserved intact, a purity that plastic or aluminum has yet to fully replicate. Eating a banana means throwing away the peel. That's obvious. But did you know that in many tropical countries, especially the Philippines and India, nothing from this zero-waste plant is discarded, not even the trunk? What was once cut down and left behind after each harvest is now collected, stripped into fiber, and recycled into high-value natural materials, generating tens of millions of US dollars each year for local communities. In the Philippines, the cradle of the global banana fiber industry, the Abaca banana is cultivated exclusively for fiber across hundreds of thousands of hectares, providing livelihoods for more than 1 million farmers and rural workers. Each year, this fiber brings in over 100 million USD for the Philippines and is recognized worldwide as one of the most durable, water-resistant, and strategically valuable natural fibers in the world. To produce natural banana fiber, the first step begins right in the field. After the banana bunches are harvested, the trunk is immediately cut down while the fiber content is at its optimal quality. A single decisive and precise cut is enough to bring down a banana trunk weighing dozens of kilograms. No machine can replace the hands and experience of farmers at this stage, as even a slight mistake in timing or cutting angle can significantly reduce the quality of the fiber obtained. After being cut down, the entire banana trunk is quickly loaded onto trucks and transported to a pre-processing facility near the field as fast as possible to prevent moisture loss and fiber oxidation. At this stage, the banana trunk is split lengthwise and peeled into individual sheaths. This is a critical step that directly determines the length and uniformity of the fiber, requiring steady hand control and practical experience. Ideally, the outer sheaths, where the cellulose fiber bundles are fully developed, yield the longest, strongest fibers with the least impurities. Farmers use specialized knives to carefully separate each layer along the natural fiber grain, avoiding damage or breakage to the fiber bundles inside. Despite modern tools, this step remains difficult to automate, as variations in trunk thickness and fiber structure still require human judgment. Each banana sheath is fed through a mechanical press or a manual stripping table to remove the soft pulp, leaving behind long bundles of cellulose fibers. Steady hand movements and precisely controlled pressure prevent the fibers from breaking, producing rough fiber strands with a characteristic ivory color. In practice, this work is far from easy, as the worker's sense of pressure combined with a consistent rhythm is a skill that often takes years for newcomers to master. After several hours of continuous processing, the result is bundles of raw fibers free of sap and retaining their full length, but still high in moisture and prone to discoloration if not washed and treated promptly. The raw fibers are then washed repeatedly with clean water, sometimes combined with mild biological enzymes to remove sap and impurities without damaging the fiber structure. Some facilities may use warm water to improve cleaning efficiency, or for fibers intended for paper production and coarse materials, apply stronger heat treatment to shorten processing time and reduce costs. Finally, the fibers are dried under natural sunlight or at low temperatures until they reach standard moisture levels, a process that typically takes at least 2 days. In major banana-growing countries, such as the Philippines, India, and Indonesia, banana fibers are traditionally sun-dried on bamboo racks or raised wooden frames under natural sunlight, allowing the fibers to dry evenly while maintaining their light color and strength. Once dried, the banana fibers become lightweight, durable, and flexible, ready to move on to sorting, spinning, and industrial production stages. Tens of thousands of tons of banana fiber are collected and sent to industrial textile mills and fiber processing facilities, where it is determined whether they will become fabric, rope, or natural mats. Once inside the factory, raw banana fiber must undergo the most fundamental and critical step, carding. Here, fiber bundles are loosened, straightened, and aligned in parallel, while short fibers, broken strands, and remaining impurities are removed. This process standardizes fiber length, fineness, and uniformity, creating a solid technical foundation for the subsequent spinning and weaving stages. After carding, the fibers are fed into the spinning system, where they are twisted under tightly controlled tension and speed. In actual production, banana fiber is rarely used in its 100% form, but is commonly blended with cotton, linen, or other bio-based fibers to enhance softness, strength, and weavability, meeting the demands of industrial manufacturing. The result is stable yarn wound into spools, ready for weaving, carpet making, or the production of finished textile products. Depending on the intended use, the yarn is fed into shuttle looms, knitting machines, or braiding machines to produce fabrics, bags, mats, or technical materials. Compared to cotton, this material stands out for its higher tensile strength, but requires blending to improve softness. When compared with jute, banana fiber is lighter and more flexible, allowing it to be used in products with higher aesthetic requirements. In packaging and interior applications, its load-bearing capacity and stability in humid environments give it an advantage over many other plant-based fibers. In sustainable fashion, it is seen as an intermediate option, balancing performance and environmental impact. In terms of cost, a garment made from banana fiber or banana-blended yarn currently sells for about 20 to 40% more than a standard cotton garment, due to higher collection and processing costs and the still limited scale of production. This remains the main barrier preventing banana fiber from becoming mainstream, as supply chains are still in the process of expansion and optimization. Each year, hundreds of millions of tons of banana trunks are reused instead of being burned, helping to reduce emissions by 20 to 30% in countries where bananas are a major crop. Easing environmental pressure and turning agricultural byproducts into part of the solution for a global green economy. According to the United Nations, more than 400 million tons of plastic are discarded worldwide each year, much of it persisting in the environment for hundreds of years, forcing humanity to seek solutions based on natural materials as practical and necessary alternatives. Among zero-waste materials, bamboo has emerged as a leading choice thanks to its rapid renewability, high durability, and low environmental impact. And one of the most talked about household items today is the bamboo toothbrush. To produce toothbrush handles that meet quality standards, bamboo selected must be 3 to 5 years old, when the fiber structure has fully developed and reached its highest stability. After harvesting, the bamboo is transported to the factory and cut into moderately long sections suitable for preliminary processing. These sections are then split lengthwise into uniform billets with consistent cross-sections. The entire cutting and splitting process is automated using industrial saws, splitting machines, and conveyor systems, ensuring high precision, stable output, and reduced material waste. Next, the bamboo is soaked in a mild biological solution to remove natural starch and sugars, preventing mold and insect infestation. This step is critical to the product's durability and safety in use. After drying and reaching the required moisture level, the bamboo is shaped into handles. Each bamboo blank is fed into the machine and cut, contoured, and rounded according to preset molds, forming ergonomic handle shapes that fit comfortably in the user's hand and meet everyday use standards. Advances in CNC machines and automated sanding technology make this process more precise, consistent, and efficient, while also reducing material waste. The head of the handle is drilled with small holes in a standardized layout, preparing it for the bristle insertion stage. This step is carried out using high-speed CNC drilling machines capable of producing hundreds of holes per minute with near-perfect precision. Thanks to advanced automated control systems and sensors, the position and depth of each hole are fully synchronized, ensuring consistent quality at industrial scale. The next step is bristle insertion. Despite being an environmentally friendly product, the bristles of bamboo toothbrushes are still primarily made from nylon, a limitation that has yet to be fully replaced. This is because nylon currently offers the best combination of durability, elasticity, and safety for gums according to dental standards. However, compared to conventional plastic toothbrushes, bamboo handles are biodegradable, significantly reducing the amount of plastic waste remaining after use. After bristle insertion, an automated trimming and polishing system evens out the bristle length and rounds the tips, ensuring a smooth surface and safe contact with the gums in accordance with dental standards. Once completed, the toothbrush is printed with brand logos using automated inkjet printing or laser engraving, ensuring clear, consistent, and long-lasting markings on the bamboo surface. Finally, the toothbrushes are sterilized and inspected for bristle retention and surface finish before being packaged in paper-based or recycled materials, minimizing the use of plastic. For green consumers and those who favor environmentally friendly products, the loofah sponge has long become a natural alternative to convenient but polluting plastic sponges. From just a mature loofah gourd, people can create sponges made 100% from natural cellulose fibers, free from microplastics and chemicals, and fully biodegradable after use. India is considered a pioneer in the cultivation and commercialization of loofah sponges, long before this product spread to the United States, Europe, and other green consumer markets. To make sponges, loofah gourds are not harvested while still young like food crops, but are left to fully mature on the vine. When the outer skin gradually turns yellow-brown, signaling that the internal fibers have fully developed, farmers harvest the gourds to ensure optimal fiber strength. After harvesting, the entire gourd is peeled to remove the outer skin, leaving only the natural loofah fibers inside. These fibers are then thoroughly washed multiple times with water to remove sap, seeds, and remaining impurities, and are sun-dried naturally for about 7 to 14 days until completely dry. Once the moisture content is reduced to the required level, the fiber structure becomes lightweight, strong, and elastic, making it ready for the shaping and finishing stages. At production workshops, dried loofah fibers are cut into various shapes such as dishwashing pads, bath sponges, or skincare pads, then edge-stitched or compression molded to enhance durability and aesthetic appeal. Some products are also treated with hot water or lightly steamed to ensure hygiene before packaging. In many Asian countries where loofah is commonly grown, such as India, Vietnam, China, and South Korea, small and medium-scale loofah sponge production models can generate between USD 500 and USD 2,000 per month for households or local businesses. This is not only a low-cost and accessible business model, but also one that creates jobs in rural areas, transforms agricultural byproducts into sustainable value, and connects traditional production with global green consumer demand. Gold does not naturally appear on the Earth's surface. Before becoming gleaming bullion stored in national reserves or traded on global financial markets, it undergoes a long journey that begins at large-scale mining operations around the world. Depending on the location and depth of the ore body, gold is extracted through two primary methods: open pit mining and underground mining. With approximately 60 to 70% of global gold production coming from open-pit mining, this method has become the dominant approach in the modern gold industry, where massive machinery and advanced geological technologies determine the value of every gram of gold recovered. The open-pit gold mining process begins with stripping away the overburden that covers the ore body. All vegetation, topsoil, and barren rock are removed to expose massive open pits that can span several kilometers in width and reach hundreds of meters in depth. At major gold mines in countries such as Australia, the United States, and Peru, between 100,000 and over 500,000 tons of earth and rock may be moved every single day just to access the gold-bearing ore below, a figure that highlights the enormous scale of this mining method. Once the ore body is exposed, industrial drilling systems come into operation. Large diameter drill bits bore holes tens of meters deep into the rock, which are then loaded with explosives and detonated according to carefully calculated sequences. Blasting is not only intended to fragment the ore, but also to control ground vibrations and ensure the safety of both equipment and mine structures. The broken ore is then collected by heavy-duty hydraulic excavators and loaded onto gigantic haul trucks, each capable of carrying 200 to 400 tons of ore per trip, before being continuously transported to the crushing and processing facilities. However, not all gold deposits can be mined using open-pit methods. When ore bodies lie deep below the surface and the overlying rock is too thick, mining operations must shift to underground mining, one of the most complex and high-risk techniques in modern gold extraction. In this method, miners access ore at depths ranging from hundreds to even thousands of meters, working in dark, confined environments under immense geological pressure. Underground gold mining begins with detailed geological exploration, using core drilling, seismic surveys, and 3D modeling to accurately determine the location, thickness, and gold grade of the ore body. Based on this data, main access tunnels and secondary drifts are excavated deep into the mountain or beneath the surface, forming an extensive underground network that can extend for tens of kilometers, allowing controlled access to the gold-bearing rock. At the ore body, high-power hydraulic drilling rigs create blast holes according to carefully calculated patterns. Explosives are then loaded and detonated in a strictly controlled sequence to fracture the gold-bearing rock while maintaining the structural stability of the tunnels. After each blast, the broken ore is collected by specialized underground loaders and haul trucks, which transport it through narrow tunnel networks to the processing area. Because operations take place in confined spaces under high pressure, ventilation, lighting, drainage, and ground support systems must operate continuously. Temperatures in deep underground mines can exceed 40 degrees Celsius, while the risks of tunnel collapse, toxic gases, and flooding are ever present. As a result, underground gold mining demands rigorous operational discipline, advanced technology, and a highly trained workforce. Currently, around 30 to 40% of global gold production comes from underground mining, particularly at major mines in South Africa, Canada, and Australia. Although more costly than open-pit mining, this method enables access to deep, high-value deposits, where each ton of ore may contain only 3 to 10 grams of gold, yet still generate substantial profits. Underground gold mining is not merely a confrontation between humans and geology. It is a clear demonstration of the price humanity pays to bring each gram of gold from the darkness beneath the earth into the center of the global economy. Regardless of whether gold is mined by open pit or underground methods, the ore ultimately converges at a single destination, the processing plant. This is where the true value of the ore is released, as rocks that appear inert begin to reveal the gold hidden deep within them. At the plant, the ore is first fed into a primary crusher, where large rocks are broken down into smaller fragments. It then passes through secondary and fine grinding stages until the particle size becomes small enough for efficient gold recovery. In modern mining operations, processing plants can handle tens of thousands to hundreds of thousands of tons of ore per day, even though the average gold grade is often only 1 to 5 grams per ton of rock. After fine grinding, the gold-bearing ore is fed into vibrating screens, where particles that meet the required size move forward, while oversized material is returned for further crushing. This is the stage at which gold truly begins to separate from the surrounding rock. Properly sized ore is then mixed with water and directed into chemical agitation tanks, where cyanide is used to dissolve the gold from the host rock. In the cyanidation process, gold enters the solution and is subsequently recovered through filtration, where gold-bearing material is captured. At this stage, the recovered gold is still impure and contains residual contaminants, requiring additional refining steps to achieve high purity. Modern processing systems are capable of handling hundreds of tons of ore per day, ensuring maximum gold recovery efficiency. After the separation and refining stages, once impurities have been reduced to the lowest possible level, the gold is transferred to a furnace to enter its final shaping phase. At temperatures above 1064 degrees, the metal melts into a glowing liquid, ready for the casting process. In manual operations, metallurgists use heat-resistant ladles or specialized pouring crucibles to guide the molten gold into molds. The flow must be kept steady and continuous, as even minor irregularities can create air bubbles, internal voids, or compromise the uniformity of the gold bar. As the molten gold reaches the base of the mold, it spreads under gravity, gradually filling the predetermined shape. In modern facilities, this entire process is fully automated. Molten gold is poured with precise control into each mold, ensuring consistent weight and dimensions across every bar. Once cast, the gold enters the cooling stage, using forced air, heat-dissipating surfaces, or fine water mist, allowing the metal to solidify rapidly while maintaining a stable crystal structure. With traditional methods, gold bars are typically left to cool naturally in open air, a process that can take anywhere from several minutes to several tens of minutes depending on their size. Once cooling is complete, the bars are removed from their molds, revealing a sharp metallic luster, ready for inspection, weighing, finishing, and ultimately entry into the global circulation system. Finally, every gold bar must undergo strict inspection after casting, precise weight measurement, purity analysis, surface structure examination, and official stamping. Only when all international standards are fully met can these gold bars officially enter circulation, becoming reserve assets, investment instruments, and a benchmark of value for the global economy. Once refined to a high level of purity, gold does not remain solely in the form of large bars. It is further processed by rolling and dividing into standardized products such as mini gold bars, minted gold ingots, or industrial gold sheets. Thanks to its exceptional malleability, gold can be rolled into uniformly thin sheets, then cut, stamped, and certified directly on production lines. At the same time, a portion of refined gold is drawn into wires to produce chains and semi-finished jewelry components, ready for further shaping and design. From a single solid gold bar, this transformation allows gold to exist in many different forms, serving both investment and consumer purposes. Alongside large-scale industrial mines, artisanal gold mining continues to exist in many parts of the world, particularly in Africa, South America, and Southeast Asia. It is estimated that more than 40 million people are involved in this activity, contributing roughly 15 to 20% of global gold production. Without massive machinery or automated systems, gold is extracted using simple tools such as shovels, sluice boxes, and basic chemicals like mercury to separate gold from sediment. This lack of regulation and control has made artisanal mining a major source of environmental degradation, contaminating water systems, destroying ecosystems, and posing serious health risks to miners and surrounding communities. Yet for many impoverished regions, it remains a vital means of survival, where each tiny grain of gold carries both hope and a heavy cost. Ultimately, every gold bar is not merely a piece of refined metal, but the result of geology, technology, and the profound trade-offs the world accepts in order to preserve its value. And that is only the beginning, because once the fresh coconuts reach the processing plant, their second life truly begins. A peeling journey that reveals the precious 30% inside, while the remaining 70%, that rugged outer armor, is reborn as coconut fiber. Thousands of tons of coconut husks pour into recycling plants, stacked into massive mountains, and left under the sun for several days to reduce moisture and soften naturally before entering their transformation phase. Once they reach the ideal dryness, these seemingly useless shells are fed into industrial shredders, where blades spinning at 1200–2800 RPM relentlessly tear, slice, and break apart the tough outer layer. Thanks to the strong cutting force and multi-tier steel blades, the machines can process tons of material per hour, producing a mix of long fibers and fine cocoa dust. This step is critical. The looseness and uniformity achieved during shredding directly determine the efficiency of subsequent cleaning, drying, and fiber separation stages. Fibers that meet the standard move on to screening systems to remove dust before being sun-dried or heat-dried to reach stable moisture levels. Once complete, the coconut fiber becomes a light, durable, and resilient material, ready to be reborn as mattresses, carpets, growing media, or countless other sustainable bioproducts. After being separated from the outer husk, coconut fiber is spread across large drying yards to soak up natural sunlight, preparing it for the next crucial stage, carding. Here, fast-moving cone rollers separate clumps, stretch the fibers, and align them into smooth strands. The result is a clean, uniform fiber stream, making carding essential for the consistency required in later twisting and weaving steps. After being finely carded, the coconut fiber is transferred to the spinning system. Here, the fiber bundles are twisted into small ropes or high-strength yarns, with each rotation tightening the strands and building the durability required for demanding applications. The twisting process binds the fibers firmly together, producing cords that are strong, resilient, and capable of withstanding significant tension. These cords become the core material used for weaving coir mats. Every parameter, twist level, diameter, density, and tensile strength, is closely monitored to ensure exceptional consistency, giving the final mats superior longevity, structural stability, and outstanding surface grip. Once the finished coconut fiber yarns are ready, they are fed into large weaving frames to form mats with the required thickness, density, and decorative patterns. In this stage, the warp threads are stretched tightly across the loom, creating a firm backbone for the mat, while the weft threads are passed rhythmically through each gap. Layer by layer, the two systems interlock to build a dense, stable structure that gives coir mats their signature coarse texture and remarkable durability. Every movement of the loom, whether powered by hand or machine, is calibrated to maintain tension, spacing, and uniformity. This precision ensures that the mats remain resistant to wear, maintain excellent grip, and hold their shape even under heavy use. Weaving is the defining step where craftsmanship and mechanical accuracy converge, shaping raw fiber into a finished product. Once the weaving is complete, The mats proceed to trimming, edge reinforcement, surface finishing, and final packing for shipment. In many traditional workshops, coconut fiber ropes are spread evenly across the floor before entering the sheet forming stage, using a wooden framing tool. This specially crafted frame functions like a hand-driven mechanical mold, with parallel wooden slats set at fixed intervals to guide craftsmen as they pull each strand into place without misalignment. Every lift and drop of the frame applies just enough pressure to lock the fibers in position while forming clean, straight channels across the surface. As the frame moves, workers use wooden mallets to tap rhythmically along the mat, compressing each layer of fiber to create a uniform structure, reduce air gaps, and maintain an even thickness. The process demands a precise understanding of force, rhythm, and fiber tension, skills gained only through years of experience. Through the harmonious combination of delicate craftsmanship and the intelligent design of the wooden frame, the finished coir sheets emerge strong, yet breathable, ready for the next stage of mattress pressing or mat weaving. Yet, the production process does not end there. The light, loose fibers left behind after weaving, too thin and lacking the structural cohesion required for mattresses or mats, are collected separately and routed into an entirely different manufacturing line. Here, this material, often dismissed as mere byproduct, becomes the ideal input for modern thermoforming technology. Golden bundles of fiber are evenly spread across heavy steel molds, forming a precise base layer. When the mold closes, the fibers are subjected to intense pressure, typically between 3 and 8 tons, combined with high heat. Under these conditions, the natural lignin within the coconut husk softens and flows, binding the fibers together from within. This unique mechanism allows the material to take shape without the use of any chemical adhesives, relying solely on the coconut's own organic resin. Only a few seconds later, the mold opens to reveal fully formed biodegradable coir pots. Lightweight, breathable, well-drained, moisture-retentive, and capable of breaking down completely in soil within months. Their naturally interwoven, root-like fiber structure allows plant roots to penetrate the pot walls easily, avoiding the circling and constriction commonly seen in plastic containers. Though these pots cannot match synthetic materials in long-term outdoor durability, they dramatically reduce plastic waste and are increasingly favored by growers and nurseries worldwide. Today, these coir-based containers are exported to more than 40 countries, becoming a small but significant part of the global shift towards sustainable horticulture. The newly formed pots are then moved to the finishing table, where any excess edges are trimmed cleanly to achieve a precise, uniform shape. Each pot undergoes a final inspection for thickness, compression, and surface quality before being packed, completing the coir fiber's transformation into a fully biodegradable product. But the journey of coir doesn't end there. Humble as it has become a key material in sustainable road construction thanks to its elasticity, drainage ability, and strong soil-binding properties. Before the coir layer is installed, the roadbed is cleared, moistened, graded, and compacted to the required density. Once the roadbed has been compacted, large coir sheets are laid evenly across the surface. Workers stretch each sheet along the alignment, overlap the edges, and smooth out the entire layer so it conforms tightly to the terrain. After the sheets are positioned, metal stakes are driven through the edges to secure them in place, creating a natural stabilization layer. No plastic, no waste, and at a cost up to 60% lower, making it ideal for rural roads where budgets are limited. With the sheets anchored, the coir immediately begins to do its job, holding soil in place, reducing surface slippage, limiting edge erosion, and dispersing loads across the subgrade. Though biodegradable and temporary, this very trait makes it a sustainable material that leaves no waste behind once its purpose is fulfilled. Immediately afterward, a truck spreads crushed stone evenly over the coir layer. The stones settle through the fiber mesh and lock into its natural structure, forming an effective mechanical interlock. After the layer of crushed stone is compacted by the roller, Workers spread a layer of soil over the surface to fill the gaps and increase the stability of the roadbed. A final pass of the roller then locks the entire structure into place, forming a solid foundation for the layers that follow. Finally, asphalt is laid over the compacted base, completing the road surface with a durable, weather-resistant finish.